everybody. Really excited to share our work with all of you today. I'm Cynthia. I'm with the GRASP Lab at the University of Pennsylvania, and I wanted to show some of the work that we've been doing. You've already seen some great introductions from Robert and Hugo on different types of ways that we can actuate robotic systems, soft robotic systems. And I wanted to bring up today a different aspect of soft robotics, starting with this video as a motivator. Some of you may have seen this video before. Those of you who haven't, though, what is this video? You can just call it out. I hear fish, right? So this is an overhead view of a fish swimming in some fluid that has flow in it, right? And you see the fish kind of swimming to the left of the video before it turns back and then starts over. But now I'm going to add in the title of the paper that this video came from. And you'll notice that the title is Passive Propulsion in Vortex Wakes. So actually, this is not a video of just a fish. This is a video of a dead fish, right? And what's happening here is that there's flow in this fluid, and the fish's body, which is not being actuated, is passively interacting with this flow in order to create this propulsion. And so there's really interesting effects in this system which have to do with the interaction between this soft body and this soft environment that allow it to be able to swim. And so what I wanted to talk about today is that in soft robotics, what we've heard about already is a lot of really cool actuation systems, and actuation is only the beginning of the story. In particular, when we think about soft robotics and about how we can get robust and efficient task execution, there's the robot and there's the environment. And oftentimes we think about how the robot is going to do work on the environment in order to perform a particular task. But actually, in the same way that the robot interacts with the environment is affecting the response from the robot itself. And this combination of the two is what we call embodied intelligence. Not only that, but in soft robotics, because you have forces, or rather stresses, that are distributed throughout the entire body, this embodied intelligence is also potentially distributed intelligence. And being able to design these sorts of soft robotic systems requires us to be able to reason about this two-way interaction. And so we've been really interested in trying to investigate this two-way interaction. I'm going to bring back this video of this fish, where actually there are a lot of really interesting questions that go into how do we not just understand this interaction, but how do we manipulate this interaction in order to get particular desired responses. So within the context of this system, for example, there are questions such as, what is a good shape or morphology that allows this fish to swim forward? Where are the actuators placed and which ones are actually necessary in order to get this robot to swim effectively? And what is the control strategy it takes once it has those actuators? So we've been interested in exploring these sorts of questions, not on fish, but I'm going to show you a different underwater system that we've been very inspired by instead. And these are salps. So how many people here have heard of salps? Okay, few hands. So salps are these underwater jellies. They're tubular in structure. You can see a picture here of a salp chain on a person's hand for scale. They're somewhere between 1 centimeter and 10 centimeters in size. But they use their tubular bodies in order to create jets. And what's really interesting about them is that these organisms are some of the most energy-efficient jet-propelled swimmers in the ocean. The only one that is beating it in terms of cost of transport, on this plot at least, is the jellyfish right here, which doesn't actually swim that fast in the first place. And so we're really interested in seeing how these salps are able to get such energy-efficient swimming. Now, the salps are interesting in that actually there are a whole bunch of different organisms, but they're connected physically together into these colonies. And chains of 80 to 100 of them swim together as a group. And if you take a closer look at how these salps are swimming, you can notice a lot of insights about how they're controlling and how they're arranged. First of all, they are organized in this kind of regular chain, but the chain isn't required to be regular. There are actually some units here that are missing. Like you see a hole right here, and the whole chain swims just fine. The other interesting insight is that actually not all of them are active at the same time, and also, unlike a lot of work that we see in multi-robot systems, these units don't synchronize. So actually, sometimes as few as 10% of them are active, and they drag the rest of the inactive SALPs around. And also, when they're jetting, they jet at phase offsets relative to each other. Why do they do that? Well, that's the question that we wanted to explore. And so what we've been working on is this robotic SALP project. SALP, in our case now, stands for SALP-Inspired Approach to Low Energy Propulsion. But it's basically this modular robotic system that we're interested in thinking about how do different robots interact with each other and the fluid to be able to create multi-robot propulsion. So this is the SALP system. I'm not, should be a video. Yes, this is the SALP system. It's basically this compliant skin that compresses and then releases it in length. When it does that, the robot changes volume. It creates a jet that is expelled out the back of the robot, and in that way, the robot can swim forward. These robots, then, we can connect them to each other in different arrangements to be able to see how multiple robots interact. And so what we've done is we've started to take a look at what those interactions are. We can attach the robots in different ways. What you're seeing is two different arrangements that we've looked at, one with the two robots aligned, one with them offset from each other, as well as different ways in which these robots can control themselves. So we can have one robot creating a jet, first contracting, and then releasing, and then contracting again, and then releasing, and the other robot offset by a certain amount in order to create a jet with some difference in timing. And what we find is that when we run this system and we measure the performance of the system, that actually, depending on what the physical offset is, this is either when they're aligned or when they're a half body length apart, and what their control offset is, this is the difference in phase between the jetting behavior, we see different amounts of power consumption, different steady state velocities, and different cost of transport. In particular, for each physical offset, there is a particular control policy that gives you the lowest cost of transport and the highest velocity. And so where does this difference in performance come from? It comes from the interaction between the robot and the environment. And so these are videos of the, basically the behavior of the fluid as the robot is creating this jet. We took these in a particle image velocimetry system. They're neutrally buoyant particles in the water that are illuminated, and we take a video of it to see what the fluid flow is. So what you're seeing on the left is what happens with a single robot. What you're seeing on the right is what happens when we have two robots next to each other. And over here, on the top video, is what happens when the two robots jet in sync. And down here, you see what happens when they jet exactly out of phase. And what happens is that when the robots are jetting in sync, these jets interact with each other. There is interference between the jets, there's a loss of energy, and as a result, a loss in thrust. Whereas when the robots are not jetting at the same time, there is much more separation between their jets and therefore more energy efficiency. So actually, the way that we arrange these robots physically and the way that we control them have a huge effect on their interaction with the fluidic environment and also with each other. Not only that, but we can also see the effects when they are now offset from each other. So in this case, this is the best case scenario when the robots are aligned, and this is the best case scenario when they're offset. We see that in both of these cases, there is a temporal separation between the jets that are being emitted, but more importantly, there's a distance between the vortices that are being emitted from these robots that give us this difference in performance compared to other control modes. Further, we see that there's a difference in the optimal velocity and control and cost of transport, the control policy that gives you the best velocity and the cost of transport between the two different physical arrangements. And this difference in performance, we think, has to do with how these jets are creating torques on the system in order to create either forward motion or different turning. And so To bring this back then to soft robotic systems, we think that these initial experiments that we've done really show us that not only is the design of the robot and our actuation and our ability to control them important, but thinking about how these robots affect the environment they're in and how the environment affects the robot has a huge effect on their ability to perform a task. If we look at the biological systems, then we also see a huge range of morphologies in cell colonies that also, we can see, has an effect on their performance in the natural world. So these are a whole bunch of different physical architectures that you'll see in cell colonies in the ocean. These were pictures taken by Kelly Sutherland, one of our collaborator at the University of Oregon, who is a salp biologist. And she's seen that for these different types of physical arrangements, some of them are better at getting higher speeds, some of them are better at being more agile, some of them are potentially better at feeding. And so there are different reasons why these biological systems might choose these different morphologies. But in any case, depending on what the morphology is, we can see that the magnitude of change in their performance increases as the number of units change. And this is when we start to see the effect of more and more interactions between the different units operating in the system. So to bring this back to then where I started this talk, which is thinking about designing these sorts of robots, I think we can learn from these sorts of interactions that there are a lot of different questions that we need to deal with when designing soft robots. When it comes to the solitary robots, there are already interesting questions of how we take advantage of robot-environment interactions in order to do things like create effective mechanisms that improve our power efficiency, or optimizing the robot mechanics in order to be able to manipulate those interactions, or how we think about which actuators that we heard in the previous talk are able to give us those types of agile locomotion. But as we also start to think about many robots interacting with the environment and with each other, there are also really interesting questions about how we can manipulate the robot environment-robot interaction in order to think about how do the morphologies of these jetting systems affect their potential for swimming locomotion, what controllers are needed to support these different morphological configurations, and what is the coupling between the physical arrangement and the controller. And to lead into the next talk after me, what are the sensing and communication requirements that are needed for these sorts of systems? So one thing I didn't talk about is that in this case, we just hardwired the robots together and we decided what is the phase offset that we're going to be used for the jetting. But practically, there's a lot of information also in the environment that these robots can use to be able to figure out what their neighboring units are doing. And so there are ways that we can think about not just active communication and coordination in these systems, but also using sensing to do passive communication and coordination in these systems that we can use for future soft robots. So that's about multi-jet swimming robots. I need to acknowledge the students in my group who worked on this project, in particular Annie, who's been leading this whole effort on creating multi-jetting robots, but also all of the other students who contributed to the hardware and the experiments. And with that, I'm happy to answer any questions.
Yeah, fascinating. Question. We have time for a couple of quick questions. If not, I have a question for Cynthia. So you demonstrated different arrangement, different species have a different arrangement of the part of the bodies. So do you know if there is a relation with external environment, external condition, with the fluid dynamics of the environment, and if this information can be, of course, used, exploited for the design of your robot?
Yes, so the question was about morphology of the
morphology
of
of different part that is arranged in a different way, if there is a relation with external environment, if biologists know something more about these characteristics.
Yeah, so I want to bring back then this picture here, where there's a lot that is unknown about these sorts of organisms, but they do come in a lot of different arrangements.
Yeah.
And so what biologists have seen is that depending on the arrangement of the colony, you'll see certain of them that have higher speeds, or certain of them that are able to turn more easily, certain of them that are arranged in ways that as you mentioned, the fluid dynamics is such that they're able to siphon water through their neighbors, which potentially is better for feeding, right?
Yeah.
And so there is a big interplay between the fluid dynamics and the
So
arrangement.
there is a relation also with the energy consumption.
Yes.
Yeah, it's a very interesting. Yes, please.
Yeah, a question about the multi-jet swimmers. So I understood that the side-by-side configuration when they were in phase was inefficient. And I was wondering if you had considered, I apologize if I missed it, but an inline configuration?
Inline configuration.
Yeah,
So like one right behind the other?
Yeah, so that you get sort of constructive interference of the vortex rings.
Yes, so we have not tried that, mostly because we expect that there's going to be interference between the robot in the back and the jets that's being generated by the robot in the front. And so far, we've only been looking at robots that are side by side but offset, but not one behind the other.
Okay, so thank you. We have to move to the next speaker. Thank you.